Hi everyone, this is a quick example on setting up centripetal force problems. It's kind of a simpler one just to show you the main idea. So when people talk about a centripetal force, it's really not a new force. It's not some new magical force like any other kind of force we've learned about. It's a combination of forces that act in a direction, and that direction, instead of calling it x or y, since it's towards the center of a circle that we choose the coordinate system, it's called the centripetal force. A better word might be the net force in the centripetal direction. All right? But the word centripetal force makes people believe that we're inventing some type of a new force that happens when there are circles, and that's not what we're doing. Some people refer to that as a centrifugal force, and we don't want to talk about that. That's a fictitious force that's really kind of due to inertia that people confuse with the idea of force. So we're going to stick with the idea of forces acting centripetally. That'll be one of our columns in like our T-charts that we're used to making. So the net force is really the sum of all forces, for instance, tension, gravity, or etc., forces you already know about that act in the centripetal direction. There's no such thing as the new magic centripetal force. It's the name of some of all your forces on your FBD that act centripetally. Okay, we're going to choose the positive direction for our forces, right, in a coordinate system. The positive, so when you do your FBD, we choose towards the center of the circle to be the positive direction for the components of the force. And any part of the force or any other force that might act outward from the center of the circle would be a negative force. All right, so we're going to do our F equals ma problems just as we've learned before. One direction will be centripetal, and we'll set up a coordinate system with another direction perpendicular to that direction, like x and y, and that would be for our other equation in our T-chart. So here's one quick example. It only has one dimension, centripetal, but I think it'll give you the flavor for what I am talking about. So the simplest thing might be maybe you're whirling a stone in a vertical circle, maybe like a sling or something like that. You're going to sling a rock. So you're whirling the rock around. It's in a vertical circle. And so the two interesting places that we're normally considering would be at the top of the circle. This is a string, so there's going to be tension in the string. The tension would be pulling downward, keeping the object on the circle from flying off. And also there'd be gravity, right, acting downward. So we have two forces that we already know about that act in a centripetal direction. So we can see if we set up our coordinate system on the object, there'd be a coordinate which we would call centripetal, and there'd be a coordinate perpendicular to it that we could call x in this case because it's horizontal. We'll let the mass, velocity, and the radius of the object be these quantities right here. We know that from what you've been learning, the sum of the forces in the centripetal direction should equal MAC. AC is the centripetal acceleration for an object going at a constant velocity in the centripetal direction. Okay, no tangential acceleration here. It's going at a constant velocity tangentially. So it's just an acceleration which is due to changing the direction of the velocity vector towards the center. So what we do is we set up our actual T-chart with the centripetal direction and the other perpendicular x direction. There's no forces acting perpendicular to the centripetal direction in this problem. So we don't have anything in this column. Okay, but we do have the tension inwards. So notice, even though the tension is down, right, we choose towards the direction of the center of the circle to be the positive direction for that coordinate. So the tension would be positive and gravity would both be positive in this case. Both acts towards the center. We would set that equal to MAC. Okay? So then, what we're looking for is the tension in the string. So it becomes a pretty easy problem once you figure out how you do that. And the tension plus gravity would equal mv squared over r. So when we solve for the tension, we can see we're going to have mv squared over r. That's ma minus fg. What you'd see is you'd have, here's your quantities, mass, velocity squared over the radius, minus a half times g. So that would give us a tension in the string of 19.1 newtons. All right, but what happens when it's swung all the way around and now it's at the bottom? Let's take a look at that FBD. So if we take a look at that FBD, okay, we just reverse the position of our object, we see that the tension is going to be upwards towards the center. Okay, the string's pulling up on the rock, but gravity is still down towards the center of the earth. So now they're in opposing directions. So in your T-chart, the tension's positive, but in this case, gravity's negative because it's outward, away from the center of the circle. The positive direction, right, is inward towards the center. So anything outward, like gravity in this case, would be in the negative centripetal direction. So now the only thing that changes about our equation is we have T minus Fg equals MAC. And we go do the problem in exactly the same way as we did above, but we'll get a different answer. The tension is going to be greater at the bottom, not only because the tension's holding the rock on the circle, but it's also having to support the weight of the rock itself. So at the bottom of the circle, the overall tension in the string will be more than it would be when the rock is going through the vertical part of the circle. There'll be a lot of similar vertical problems like this, like roller coasters where things are going in a circle and different things like that. And instead of tension, it'll be a normal force, right, from the surface of the roller coaster tracks. So for instance, if this was a roller coaster track, right, and we're taking a look at a circle, sorry about that, going around like this, at the bottom of the circular roller coaster track, you'd have a normal force upward and you'd have gravity downward. And so the normal force would take the place of tension, and that's why you feel heavier when you're at the bottom of the circle, because the normal force is greater. When you're at the top of a circle, like in a roller coaster cart, then what's going to happen is the normal force is downward and gravity is downward, and it's like our first tension problem. So now you see your normal force is going to be less because of what we just saw in the above work. Just like the tension is less, the normal force is taking the place of the tension, and you feel lighter as you're going through the top of a roller coaster circle. So a lot of common problems with vertical circles are done this way, so it's a good place to start. All right, hope that makes sense.